You guys, not even recording. Oh my word. What percent ionization will verapamil be at? pK 8.73 at pH of 6.2. So I'll give you a moment to work your way through that. Give you a couple minutes, and then we'll talk through that using the 5 steps that we went through last night. And then when you're all set, just let me know in the chat so that way I know how to gauge how much time people need. All right. Does anyone need just an extra moment or two? Totally fine if you do. Just let me know. Okay. Yeah. Take your time. So I'll give you a couple more minutes. All right. Let's take a look. So the way that we approach these problems is first steps first is we need to identify, do we have an acidic or basic drug? And based on what we just determined, we know that we have a basic drug. The second step is we need to choose our equilibrium equation. So for acidic drugs, what we are going to choose is acid. The drug structure with its hydrogen dissociates into drug minus plus H plus, or we can have a basic drug, which will capture the hydrogen and we get the protonated form, which is protonated. So we know that this drug is basic. So the equation that we are going to choose is the second one. So we have verapamil plus a hydrogen gives us the protonated form of the drug. Once we've done that, the next step is to label the pKa and pH. Or actually, I skipped a step. We need to label the protonated and deprotonated drug. Then we can say that the protonated drug is this one over here. So we have our protonated drug and we have our deprotonated drug. In the same way that this would be our non-ionized and our ionized drug. And then next, what we have is we're going to label the protonated drug with the pKa given in the problem, and we're going to label H+ with the pH given in the problem. So we know that the protonated drug should be 8.73, and the pH will be over here at 6.2. And the final step is that we follow Mother Nature's rule, which is that we always choose the weaker acid. The weaker acid is the molecule with the higher number. So in this case, the protonated drug has a higher value. So Mother Nature is going to choose the protonated drug. Any questions about that so far? All right. From here, we can construct and we can plug in, okay, we have 8.73 and we have 6.2. And we know that we can have 3 steps of a drug to talk about. So as we move from the pKa towards the pH, what form of the drug are we going to have? The ionized form, right? How do we know that? Because Mother Nature is telling us it's going to be the ionized form. So what we can do is we can use the rule of 10, and we can say that, okay, here we would have 10 over 1, then 100 over 1, and then 1,000 over 1. So our pH falls in between 100 over 1 and 1,000 over 1, which means that this would be 99% and 100% or 99.9%. So what this is telling me is that at a pH of 6.2, 99 to 100% of the drug will be ionized. And so this is how we can approach these pKa problems and get the correct answer every time. This is what you guys wanted to go over, right? These sorts of problems?
Yeah, that's good.
Okay. All right. Any questions about this problem? All right. I am going to give you another drug. There is a drug called penicillin.
Sorry, I'm actually just confused. How would it be ionized since you're moving like to the left and you're doing 10 over 1? Is it?
This is a slightly different approach than how Dr. Mahana describes it in the class notes, where what we're always describing the numerator as the form of the drug that is predicted by the equation. So I think what Dr. Mahana would have is 1/10 and 1/100, 1/1000, which either one of these would produce the correct answer. What's important to know here is that using this method, no matter which direction you point the arrow, the form that is happening is determined by the mother nature. Does that make sense? Kind of?
Kind of, yeah.
Okay. What I would recommend is take a look at the video last night, because someone had a very similar question, and we went more in depth on it as well.
For his like questions, does he specify like when he puts like the choice answers, does he put ionized and unionized? Because he didn't in his like study guide questions.
Yes, he will. Yeah. And so the next problem we're looking at, I'll give you some multiple choice questions to choose from. Good questions. All right. So I have penicillin VK. And this is actually how the drug comes, penicillin VK. Very, very heavy emphasis on the K. And this has a pKa of 2.34. And I want you to tell me what the ionization would be at a pH of 8.15. Mm. 3.15. God, Sarah, you're calling out my bad handwriting. Jeez. No, I'm just kidding. 呃 did this in my head, so we'll see if I did it right. Um, Give you one more moment. All right. So first steps first is we have to determine what kind of drug are we working with. And what we see is that this is potassium. So this would be a positive ion, which means penicillin must be negative. And so what we have going on is an acidic drug. For acidic drugs, the equation that we're going to choose is this first one here. So we would have penicillin with its hydrogen dissociating into penicillin negative plus H plus. Next, we have to label where the protonated drug would be, which would be whichever structure contains the hydrogen attached to it. So this would be deprotonated, which would mean that this is the ionized drug. And here we have the non-ionized drug, which I want you to note that up above, the protonated drug was ionized for a basic drug. But down here, the protonated drug is neutral. So just because it's protonated doesn't mean that it's always going to be ionized. It depends on what kind of drug we're working with. So don't make that assumption. From here, we can label the pH where the H plus goes. Then we can label pKa where the protonated drug is. And we follow the rule of Mother Nature, which says that we choose the higher number, which in this case would be choosing the ionized form of the drug. So we can construct our number line. And we have our pKa at 2.34, which would mean that we can go to 3.34, 3.34, 4.34, 5.34. And our pH is found right here, 3.15. So what is going on here? Well, at the pKa, we have 50 over 50, right? Whereas at 3.14, we would have 10 over 1. So we would be between 50% and 90% ionized. How do we know it's ionized? Because Mother Nature told us that it's 50 to 90% ionized. What would be the reverse of this is saying 10 to 50% non-ionized. These are both true statements, right? Because one is accounting for what Mother Nature is choosing, the other is for what Mother Nature is not choosing. So in terms of these questions, the best answer would be A. But if there was a select all that apply and had another one that was 10 to 50% non-ionized, that would also be a valid answer for a select all that apply. Does that make sense? Does this give you kind of a better idea of what the questions are going to be like in the exam? Any questions? Good question. Why does it want the ionized form? Mother Nature will always, always, always choose the weaker acid, right? And the weaker acid is going to be the higher number. So that's why we chose the ionized site. So the equation up here tells us what is the preferred structure. And then the number line tells us what the numbers will be, the percentages. Good question. All right, let's do another question. Let me go back to, let's do nicotine. Huge. All right, what I want you to do is I want you to tell me what are all the valid metabolic pathways. And I am just labeling some carbons for us. Aromatic hydroxylation, 100%. Yeah. And what would be the preferred carbon for aromatic hydroxylation? Carbon 4 would be a good option. What would be almost as good of an option as carbon 4? Maybe even a little bit better if I could see some of the data. Carbon 6. Why? Because it's para to the nitrogen in the ring. Yeah. So even a substitution within the ring can help dictate where para goes. Now, would you have to choose on the exam, oh, is it going to be 4 or is it going to be 6? No, you don't need to do that on the exam. That's not part of the content for this class. What you would need to be able to do, though, is that if he gave you, a list of structures and said, select all the valid structures, you would need to be able to identify that OH could go in the 4th position or it could go in the 6th position. What else? What else is a valid metabolic pathway? Yeah, N-demethylation. 100%. I would agree. All right. What functional groups are present in caffeine? What functional groups are present? I see tertiary amine. Yep. We have this methyl group here, 100%. What else do we have going on in caffeine? Very nice. We have pyridine. I always get questions from students about, are there any tricks to memorizing the heterocycles? Kaylee, I think, actually came up with one, and she, if you're able to upload that to the classroom, Kaylee, I think a lot of people would benefit from that. But really, there's no trick other than just memorizing them. This is one of those times where it is just straight memorization, unfortunately enough. Oh, did I say nicotine or? Oh, my bad. Nope, this is this is nicotine. Me not paying attention. Not caffeine. I'm thinking about what I want right now. All right. Tell me what the percent ionization of nicotine, which we're going to say has a pKa of 7.95 at a pH of, let's say, someone who's slightly acidotic. Slightly, that's very acidotic. 7.15. No. 5.85. So the end of the middle of the jejunum. $99 to $100. I'm going to say that is a incorrect answer. It is a base. Yep, it is basic. I'll give a. All will be revealed. No, you know, 99 to 99.9. You know that. You know, but you're missing a crucial piece of information to answer this question. Um, 0 to 1%, again, I would say is a incorrect answer. You all are thinking like, what the fuck is he talking about? All right, let's talk about this. So first things first, we need to identify acidic or basic. People correctly pointed out that nicotine has a tertiary amine, which would tell us it's basic, which means that our equation is going to be nicotine plus a hydrogen creates the protonated form of the drug. So this would be our protonated and our ionized form. And so we would label this side with our pKa, 7.95, and we would label our pH, 5.85. Mother Nature will always, always, always choose the weaker acid, which in this case is the protonated form of the drug. So Mother Nature at this specific pH will choose the drug that is in its ionized form. So we look at our number line. We have 7.95. We also have 7.95. 6.95, 5.95, 4.95, and our pH falls in 5.85, be somewhere about here, right? Am I crazy? 5.85, yep. So we can fill this in and say that this would be 50-50. This would be 90%. This would be 99%. And then we have 100%. So the answer here would be 99 to 100% ionized. You have to tell me what it is. The reason why I'm being this stingy is because I don't know if potentially on the exam he makes this open response and he says, write in the answer. Because if you write in 99 to 100% ionized, if you just report the percentage, you're not actually telling me what the answer is. So why do we not include the 50%? I see what you're saying. Great question. Why do we start at the pKa? The reason why we start at the pKa is because we jump 3 times from the pKa in the direction that the pH is. So this would be 1 jump, a second jump, and 3 jumps. So what would have helped is if I did this in 3 colors, right? So here's my pKa, here's my 3 jumps, and then here is my pH. I would include like 50 to 90% if my pH fell within this range, within this quadrant. So it depends on where your pH is falling. All
And
right.
so,
Yep.
on the scale here, because the ionized form is preferred, we go from the pKa, then we do the jumps, right?
Yes. Yep.
Yeah.
And so the numbers that are reported here, the 90, 99%, 100%, is always based off what Mother Nature told us. If you want the opposite to this, you find this number and then you take the opposite, 0 to 1%.
Got it. Thank you.
No problem. Any other questions about pKa, pH problems, that kind of stuff? Do we kind of understand the general approach, that sort of thing? Okay. Do we want to do one more, or do we want to move on to other metabolism questions? One more? Okay. All right. Ooh, metabuterenol. Metabuterenol.
Correct that. It's supposed to be proterenol. Yeah.
Okay. All right.
Hey.
I'm gonna do this. And what I am also going to grab is this label. So here we have metaproterenol. And what I want you to do is I want you to first identify all the functional groups. Then I want you to identify what the potential metabolic pathways would be. And then lastly, I want you to figure out with a pKa of, I don't know, probably somewhere around 8.4 at a pH of 10.3. So I'll give you a few minutes to work your way through this. And while you guys are doing that, I'm going to run to the bathroom real quick. So I will be right back. I am back. Is the parent nucleus benzene or phenol? I think the parent would technically be an alpha beta aminol because you have the nitrogen, the amine moiety adjacent to the hydroxide, but I could see it being classified as a phenol drug because it has that kind of ability. I think this is called a 1,3 catechol though. But again, determining like parent structure isn't on the exam. But I think it would be either a 1,3 catechol or it would be an alpha beta aminol. Technically. It's close to being a catechol. Catechol is where if you had it on position 3 and 4, but we have like position 3 and 5. So it's close to being one. It would probably act somewhat similarly. But all right, so let's talk through this. So major functional groups that we have in here is we have a benzene ring, but more specifically and probably more importantly, we have a phenol. So on the exam, he's not going to, he might have a select all that apply that is benzene, phenol. Just if you see it, click it, so we have both a benzene ring and we have a phenol. We also have here an amine. Yes, click both if both are available. Yeah. It would kind of be redundant because technically a phenol is it's a phenyl alcohol, but who knows what he's doing. I don't think he would put both though. What kind of amine is this? Is it primary, secondary? Yeah, this would be secondary. And if you're wondering how you determine this, what you do is you put a box around the nitrogen and you say how many things are bonded into the box that are not hydrogen. And what we see is that we have 2 things, so this would be secondary. And then if you wanted, we could also classify this, we have an alcohol or a hydroxyl group. Technically, it's a secondary alcohol, but I don't think you need to classify alcohols for the exam. I might be mistaken though. So what are our valid metabolic pathways? What do people come up with?
Hydroxylation.
What kind of hydroxylation? So there is a possibility of aromatic hydroxylation, primarily because we have this open para position, right? That would be a very, very good indication that we could do aromatic hydroxylation. Would we necessarily expect it to do it? Maybe not, because there's already some OHs on there, but it is definitely a valid pathway. We also have a dealkylization, specifically what kind of ND what? What group are we removing here?
Isopropyl.
Yeah, so we see that we have, oops, that's a terrible color. We have 1, 2, 3 carbons in this kind of, and we're bonding into the middle carbon. So this would be ND isopropylation. Often one of the things I see people fall into the trap of is just going, oh, it's N-demethylation. No. Demethylation is only on a methyl group. I have seen on exams where he will put N-demethylation or ND isopropylation, and just to catch students who are just applying things broadly. The other thing that can happen is direct phase 2. Direct phase 2. Could it be aliphatic hydroxylation? Yeah, it's possible. I wouldn't say it's very likely because unlike the other situation for verapamil, we just had carbon chains leading up to that isopropyl group. So, this position was just a carbon, whereas here, this position is a nitrogen, so it makes that a little bit wonky. But could you get aliphatic hydroxylation here? Yeah, it's possible. If it was an option, I would choose it. And then, of course, we have open OH-NH bonds, so this could go directly to phase 2. Very nice. All right. Is this an acidic or basic drug. Aliphatic, you need it to be longer than ethyl. So longer than 2 carbons, so isopropyl is 3. It's tough, but it can happen, I believe. So what kind of drug is this? Acidic or basic? Yeah. So the reason why I put the label in here for us is because if we look at just the structure alone, we see we have this amine, which would be basic, but we also, based on the packet, phenol is an acidic functional group. So essentially, we have 2 acidic functional groups and 1 basic functional group. So just looking at the structure alone, it would be pretty difficult to determine what the acidity or basicity of the drug would be. So that's why I included the label here, which tells us that we have sulfate. Can you do MAO or not, because it's not the right functional group? Yeah, so MAO would require a terminal amine. MAO would require just regular old NH2 coming off of a chain. Good question. So we see that it's sulfate. Sulfate tells us that this is a negative salt. Could it be COMT? COMT, same thing. It would need to be an internal NH2. So no conjugation on the NH2. Oh, catechol. Oh, sorry. I'm thinking of oxidative deamination. Catechol O-methyltransferase. Could it do? No. COMT only works on catechols, which would require this adjacent OH. There is a different enzyme that works on this sort of arrangement, but I don't think it's COMT. At least for what you guys have to know, it's not COMT. Good question, though. So we have a negative salt, which would mean that isoproterenol, metaproterenol, sorry, is positive, which would tell me that this is a basic drug overall, right? So we would have meta plus H plus becomes meta H. Here we would have the protonated drug, which is also the, forgot my plus sign, which is also the ionized form of the drug. It's possible for it to go under aliphatic. It would not be very favored, purely because we have this nitrogen here. But if it was an option on the exam, would I choose it? Probably. It wouldn't be my first choice, and I would only do it if it was select all then apply, because these other ones are much better answers, but I wouldn't not pick it for select all then apply. So we can plug in the pH here at 10.3, the pKa at 8.4. And so Mother Nature will always choose the higher number, which is the weaker acid. So Mother Nature is going to choose the non-ionized form of the drug at a pH of 10.3. So we have 0 to 14. We have 8.4, which is the pKa. Then we have 9.4, 10.4, 11.4, which is our 3 jumps. And then we have our pH, which corresponds to 10.3. And so what we can say is that at the pKa, we would have 50%. Then we'd have 90%, then 99%, then 100%. So we fall in between the 90 to 99% range, which would be 90 to 99% non-ionized. How do I know it's non-ionized? Because the equation chose the non-ionized form. Any questions about this? All right. I want to go through a couple of questions I threw up on the classroom here, just because I think that they talk about some good concepts for us. All right. So for this problem, we're looking to improve the half-life of phenytoin. So I showed you the metabolism of phenytoin, which is aromatic hydroxylation, putting an OH para to the hydantoin nucleus. So that, para to the drug. How could we improve the molecule in order to make the half-life better? So in other words, how could we inhibit this metabolism in order to make the half-life better? What do we think? Which structure would improve the half-life by inhibiting that metabolism? Make it more lipophilic. It's an option. Yep. But how can we specifically prevent this reaction? How could we specifically prevent it? ECB, DBA. I think once we talk about this, you guys will have a pretty good idea. I'll give another minute just to think about it a little bit. That's kind of too big. Can we do? There we go. Much better. So when we talk about improving half-life, right? If we want to improve the half-life of a drug, what we are trying to do is we're trying to decrease metabolism. Half-life is a measure of how long the drug stays in the body. And one of the ways that a drug leaves the body is through metabolism. So if we want to make it hang around longer, we have to prevent metabolism. What do we know would happen to this drug once it reaches this structure? What is most likely going to happen next? So here we had aromatic hydroxylation, which is a phase 1 reaction. So what normally happens after phase 1? We get phase 2, right? So some sort of conjugation with glucuronic acid or maybe sulfation, some sort of conjugation which is going to make it very, very water soluble, and then we put it in the pee, right? We love putting things in our pee. So because of that, if we had a structure that could, prevent either this or prevent this, we would improve the half-life, right? Because either one of these steps will result in metabolism. So our goal is to prevent metabolism. So let's look at structure A real quick. Why would A not really improve metabolism? What can happen to structure A that is different than the original phenytoin? Yeah, this goes directly through phase 2. If I can skip phase 1, I'm not making it hang around any faster. In fact, I am increasing the elimination of the drug and increasing metabolism. So putting a very polar group that's easy to conjugate does not improve half-life. Looking at structure D, right, one of the things that we want to see is preventing this para position, right? But if we look at structure D, are we really preventing aromatic hydroxylation? Nope, not at all. So we would still get aromatic hydroxylation. And in fact, we probably wouldn't be really doing that much for half-life. Does that make sense? Does anybody have questions about that? So it's not going to be A and it's not going to be D. If we look at E, E is just swapping one aromatic ring for another aromatic ring, which would mean that we could put an OH right here. So are we in fact preventing aromatic hydroxylation? Nope, we're just changing the way that it would look. So E is not a good replacement because we're still going to get aromatic hydroxylation. Or, and the other possibility is it could go there, either one. So now it comes down to B and C. Both B and C prevent the para position. So they're going to prevent the aromatic hydroxylation, its preferred site. But what can happen to this isopropyl group that we know cannot happen to a fluorine? What could potentially happen to the isopropyl group? aliphatic hydroxylation. Remember, dealkylization, if we're talking about deisopropylation, for example, remember that we need to talk about, what atom is it being removed from? So that isopropyl group would need to be connected to a nitrogen or an oxygen or something like that. So in order to do deisopropylation, you need to have N-deisopropyl or OD, but we can see that it's not connected to anything. There's only carbons there. Does that make sense for people? Why it's not deisopropyl? So it's not that guy. Exactly. So it would be B. Are there any metabolic pathways that we have learned that get rid of halogens? Do we know how to get rid of halogens? Nope. Do not ever try to remove a halogen from a drug. You do not know how. Neither do I, actually. So if you ever have a pathway that tries to get rid of a halogen, it's wrong. We do not know how to get rid of halogens. So this fluorine is preventing, I'll do it up here. So this is preventing the aromatic hydroxylation without adding other pathways. And just like Tati said, yes, of course, it would just go to the other one, for any of these. But, I'm just keeping, they're all consistent across them. So, but yes, it would just go to the other benzene ring, 100%. This is definitely a harder problem than what you would see on the exam. But it illustrates the idea of making changes to a drug, which is the backbone of medicinal chemistry. Medicinal chemistry is all about modifying structures. So being able to look at a structure and how to prevent metabolism is just as important as talking about ways of how it is metabolized. So because of that, what I want us to do is I want us to take a look at one of your drugs on your list. So taking the structure of morphine, what I want you to think about is what are ways to decrease metabolism in order to increase half-life. So here we have morphine. So what would be some modifications we could make to morphine in order to prevent potential metabolic pathways? And I will put some So I saw add halogens to carbon C or D, I would 100% agree. So one of the potential metabolic pathways is aromatic hydroxylation. So putting some fluorine, that is a totally a potential. Make it into heroin. Yep. So how do we turn it into heroin? I saw put methyl or ethyl groups. Yeah. Add ethers, right? So instead of an OH group, which would directly conjugate, we could turn this into OCH3, right? Because then it would have to go through demethylation. Totally. Yeah, or another option is we could use an ester, right? So we could add an acetyl group, for example. And so what that would do is this would require esterase to come in and remove this ester moiety. Yeah. So what else? What else could improve the half-life? Specifically, oh, sorry, I'll write this in. Add esters or ethers. Either one. Either one is valid. What about specifically about this nitrogen here? How could we modify what's going on with the nitrogen to help improve metabolism? Well, yeah, make this super long and branched, right? So if you make this super complicated, then so if you make the complicated branching, you are going to prevent simple demethylation, right? To improve half-life. So to improve half-life, we're going to decrease metabolism. So one of the ways that we could potentially do this is make it more branched, right? Because then it would prevent that group from being removed and then potentially sent through metabolism. Yes, so this is a really good question. So what esters do is that they improve, esters improve the lipophilicity of a drug. But they, because it is technically a metabolic step, even though it's very, very, very fast ester hydrolysis, it would still be something that the body would need to take care of in order to interact with that oxygen. So even though ester hydrolysis is a very, very fast reaction, it is something that would technically increase metabolism just very minorly. Does that answer your question? Same thing if we did like it in a mid. So what is the implications of this? I just want to show you real quick. Codeine is the methyl form of, here we go. Codeine is the methyl form of morphine, and heroin is the acetylated form of morphine. So codeine and heroin are the same thing. They're just slightly modified. structures of morphine. Kind of cool. All right. Let us talk about this one. So for this one, the question is, which drugs would undergo would not do aromatic hydroxylation? Which drugs are not really able to undergo aromatic hydroxylation? Norepi, yeah, I'd say norepi is a valid option. Yep, it's also select all that apply here as well, I should say. So I'd say norepi is a potential option. Yep. Levothyroxine, definitely, because those para positions are taken up by groups already. And then I would agree that physostigmine, you might be able to get an OH here, but I'd say that it's potential. I'd say that any three of these would be potentially unable to do aromatic hydroxylation. Someone asked maybe about imipramine, and imipramine has these nice open benzene rings that it could be doing. Yes, levo is definitely an option because are you asking about like what if it's para to the iodine? That's a good question. The iodine molecules would not produce para hydroxylation. Halogens are basically like little void sections of a drug. They just prevent things from occurring. If that makes sense. It's kind of a terrible explanation, but yeah. Yep. All right. Which drugs would do oxidative deamination? So I see levo, I see potentially norepi, I see someone said maybe temazepam, I saw physo pop up. I think the only one we're missing is imipramine. So let's talk about these. So oxidative deamination, I'll do this, do it up here. Oxidative, actually, so that way I can give myself more room. Oxidative deamination is a process that requires an internal, can't spell. This requires an internal NH2. So what we're looking for is we have a carbon chain, and coming off of somewhere in the middle of the carbon chain we see just NH2. This is the only thing that we see. The comparison to this would be MaO, which requires a terminal NH2. And I know I think I talked about this wrong last night. So if someone who was here last night can just fact check me real quick, just so that way I know I'm not saying the wrong thing again. Okay, we're good. So MaO, terminal NH2. Oxidative deamination, internal NH2. So looking at these drugs one more time, which of these drugs has a internal NH2 in order to remove versus with oxidative deamination? Just levo. Exactly. Levo only. What about MaO? Which one would be MaO? Norepi. Very nice. All right. Which drugs could undergo amidase? So just to highlight what we're talking about. Which drugs could do amidase? I see Physo, imipramine potentially, temazepam I see, physostigmine. So for amidase, what we are looking for is any kind of amide. So an amide is where we have that nice carbon double bonded to an O and then a nitrogen. And usually this nitrogen will be bonded to something else, but it could be, it by itself. That's totally valid. You can also have an amide that is inside of a ring, right? If you remember from way back from Orgo, we actually talked about these. Does anybody remember the name of these? I definitely know my Orgo students, I taught these to you. So here what we have is what's called an aliphatic amide, which is basically just saying it's part of a chain. So, we see something like this. That would be an aliphatic amide. Versus a cyclic amide, which is also known as a lactam. So taking a look up here, I would agree with you. We do see an amide here. Technically, this is part of a functional group called a carbamate, but it is possible for physostigmine to be affected by amidase. Where else do we see an amide? Someone said it earlier. Yeah, we see it in temazepam. So don't discount amides just because they might be inside of a ring. They are a valid target. Why does imipramine not get metabolized by amidase? What functional groups does it have? Yeah, exactly. There's no carbonyl. There's no C double bonded to an O. It would be different if we had something like this. You know, then it could, but imipramine does not. All right, a couple more. Which drugs would undergo COMT? Catechol O-methyltransferase. Yeah, norepi. Remember that catechol is this functional group where you have a benzene ring with these two OHs next to each other. So this is what's called a catechol. And so in order to do COMT, you would need to have this catechol functional group in order to fit in the enzyme. And then finally, my last question for you is that which drugs can do direct phase 2? Definitely levo, I would agree. Norepi, yep. I would agree with temazepam. We have that nice open OH group here. How about physostigmine? Would it it's possible. I would say that it probably needs to have that methyl group removed first. I would say that if you had to pick one of them, any of these other choices is better than physostigmine. Could it? Maybe. I'm not sure. I'm not sure if carbamates do that. Yes. So this is a really great question. Terminal amides can go directly to phase 2, but internal cannot. So what that is talking about is, so the idea that aliphatic amides, ones that are at the ends of chains, these can go directly through phase 2 as long as one of the groups is a hydrogen. Versus cyclic amides like lactams are not able to go through phase 2 directly. They're too bound up. They're too, secluded inside of their ring to go through directly through phase 2. So if, for example, temazepam had an H here, this amide would not be able to go through direct phase 2 because it's too bound up. But it can go through direct phase 2 through that OH. So we have lots of options all around. Was this helpful to go through all these different drugs, by the way, like this? Okay, great. Great. Here's a great question. Easy points. Same rule for, yes. So a carboxylic acid can definitely go through phase 2 directly, whereas an ester, an ester doesn't have that OH bond, so it wouldn't be able to do the direct phase 2. It'd have to be hydrolyzed first. Yeah, good question. All right, take care, Sarah. So we'll take a look at these last 2 questions here. But which of the following enzymes are non-microsomal? So my first question is, what does a non-microsomal mean? Oh, I don't think you had to learn about alcoholic dehydrogenase. I don't think you'll interpret this. Yes, exactly. Non-microsomal. So out of, except for this one, except for that one, because that was not in your list of enzymes to care about, which one of these are non-microsomal? Exactly. Monoamine and COMT. Right. Technically, alcoholic dehydrogenases as well, but I didn't realize at the time when I made this that it wasn't in your list. Even though it's such a fun one, right? Because it's the one that drugs inhibit, and then you can't drink alcohol anymore when you throw up. All right. Which of the following enzymes would not be found in the liver generally? Which of the following would not be found in the liver generally? Someone says a drug that produces catechol. I would 100% agree. This is a drug that is not found in the liver generally. And how come? Which enzyme is that? Yeah, catechol would be COMT. An enzyme that degrades the ester functional group on a prodrug. This would definitely not be, because we know this is an esterase. Esterases are found almost ubiquitously throughout the body. How about an enzyme that transforms a primary amine into an aldehyde? Primary amine into an aldehyde. So in order to get an aldehyde would be at the end of a chain, which means that it would have to be something like this. So if we end up with an aldehyde out of our reaction from an amine, is this a terminal or internal NH2? This is terminal. And based on what we said up above, we know that if it's a terminal NH2, it would be MAO, right? So if it's MAO, we know that that takes place outside of the liver. Yeah. So MAO is outside of the liver. How about a carboxylic acid into an amide? This enzyme doesn't exist. It was a trick question. An enzyme that could be induced by the presence of a drug. This is describing all enzymes. All enzymes have the ability to be induced. It does not matter where they are. And more generally, the liver enzymes are way more likely to be induced than anything else. And then finally, how about this one? One that does not participate in first pass metabolism. What do we think? Microsomal or non-microsomal? Inside the liver or outside the liver? Yeah, so first pass metabolism, where does this happen? Where does first pass metabolism happen? In the liver, right? When drugs are absorbed from the gut, they go first to the liver to get metabolized, and then they get dumped into the blood. So if you do not participate in first pass metabolism, then you are not in the liver, which means that you are generally not there. Does that make sense? Any questions about those? All right. This is where we will wrap up for tonight. Please, please, please get some rest. Do some flashcards tonight for your heterocycles. If you have any questions, please send me an email or send me a text. All the way to the beginning real quick. Beginning of what? Beginning of this? Or the first page?
Ooh, I also had a quick question real quick too.
Yes.
So, I mean, I'll let you take care of the first one and then you can answer mine.
I think this is where Jana wanted to go. Let me know though, Jana. Yes, as soon as the recording is ready, I will put it up. Yep, as soon as it is. What's your question?
So my question was when we were on the metaprotenolol, the drug, when we did the 0 to 14 scale, you jumped from 8.4, then you did 9.4, then you did 10.4. And I was just wondering, since the non-ionized state was preferred, how come we didn't jump from 10.3 to 9.3 to 8.3?
Good question. We always base the jumps off of the pKa. The pH is fixed. It's a fixed number, but the pKa will jump.
Okay.
Good question.
All right. Okay. All right. Thank you very much, Gabe.
No problem. For people, in case if you have questions on the stream in the Google Classroom, you can, send me an email or send me a text, whatever. I will be up fairly late doing some work, so if you have any questions, feel free to send them over. But good luck on your exam. What time is it tomorrow? In the morning or 8 a.m.? Oh, great.